Welcome back to the Deep Dive. Today, we're tackling something, well, huge, literally. We're looking at gantry machining centers, GMCs.
And specifically, the choice between two main types. It's a massive decision.
Absolutely. This isn't just picking a machine. It's a multi-million-dollar investment that honestly shapes your entire operation for maybe 20 years. Get it wrong.
And you're stuck, really stuck. Either you can't hit the precision you need for certain jobs, or you just physically can't handle the larger scale work that might come your way. It's a mistake you just can't afford to make.
Exactly. So our mission today, cut through the noise. We want to give you the core differences you need to know to match the right machine architecture to your specific needs.
We're comparing the fixed beam gantry. Think of it like a solid granite bridge. Built for stability, amazing for high precision stuff like mold finishing.
Gets the moving beam gantry. That's more like maybe a versatile crane. All about flexibility, handling really big, heavy parts where the workpiece absolutely has to stay put. Think shipbuilding, that kind of scale.
Yeah, so we're going to unpack the fundamental mechanical differences, why they perform differently, and what that means for your shop floor, your foundation costs, even long-term value.
Okay, let's dive straight in then. Let's get to the absolute heart of the matter.
Yeah.
What is actually moving versus what's stationary in each design? Because, like you said, misunderstanding this basic point seems to be the root of a lot of bad choices.
It really is. It boils down to how they manage the mass. So take the fixed beam gantry. In that design, the big horizontal crossbeam, that bridge structure, it's bolted permanently to the columns, locked, solid.
Elliptical mass.
Exactly. It provides this incredibly rigid, unwavering overhead support for the cutting tool. The gantry itself doesn't go anywhere along the main axis.
Okay, so the gantry structure is static,
Mm-hmm.
but you obviously need movement along the length of the part to machine it. So how does that work?
Right. That's the key difference. The workpiece table moves. It travels along the x-axis, which is usually the long axis, carrying the part back and forth underneath that fixed gantry structure.
I see. So the workpiece itself is doing the long-distance travel.
Correct. And then the spindle, the part that holds the tool, handles the y-axis, side to side across the beam, and the z-axis up and down.
So the design philosophy there is basically keep the tool support absolutely rock solid, even if it means moving a potentially huge table and workpiece.
That's the idea. Similar mechanics in some ways for the gantry itself, focused entirely on that overhead rigidity.
But that immediately brings up a physics question, doesn't it? If you've got a massive table, maybe holding a part that weighs, 50 tons altogether, moving that back and forth quickly, that needs enormous power.
Oh, absolutely enormous. You're talking colossal drive systems, and just as critical are the control systems and the brakes needed to handle that immense inertia, starting and stopping smoothly while trying to hold micron-level positioning. That's a major engineering challenge, and expensive.
Right. Okay, so that's the fixed beam. Now let's flip to the moving beam gantry. You said the approach is reversed.
Completely reversed. Here, the workpiece sits on a stationary bed or sometimes a floor plate. The part itself does not move along the x-axis at all.
It just stays put.
Stays put.
Mm-hmm.
Instead, the entire gantry structure, that means both columns and the crossbeam, travels along rails built into the foundation. It moves in the x-axis over the stationary part.
Wow. Okay, so you're moving the whole bridge structure. That sounds mechanically more complex, maybe.
It is, in terms of driving and synchronizing that large, heavy structure accurately. But the huge advantage is the part isn't moving.
And the z-axis, the up and down.
Yeah, on the moving beam, typically the crossbeam itself moves up and down along the columns. That handles the z-axis adjustment, accommodating different part heights. It does require, precise synchronization between the drives on both columns.
But the trade-off is clear. You get maximum flexibility for part size and weight because the machine isn't trying to shuttle the part around.
Exactly. The design philosophy shifts to enabling work on virtually limitless part sizes and weights.
Okay, that clarifies the movement aspect really well. But movement directly impacts precision, right? So if you need really tight tolerances, which design inherently offers more stability, more unwavering accuracy for that high-value work?
Well, if you're purely chasing the absolute tightest tolerances, the physics really does favor the fixed beam gantry.
Because it's static.
Because it's static, that monolithic structure is just inherently more rigid. Since the main bridge isn't moving, it's incredibly good at damping out vibrations generated during the cut.
It acts like a constant, stable reference point for the tool. I can see how that's critical for things like mold and die work, where you might need micron-level accuracy and a perfect finish. That stability is everything there, isn't it?
It is, and think about thermal stability too. A massive fixed cast iron structure tends to heat up and cool down more uniformly, more slowly than a structure that's constantly moving and potentially subject to different thermal loads. That helps minimize thermal drift during long machining cycles.
Okay, that makes sense. But then you see these huge moving beam machines successfully making complex aerospace parts, like wing spars that are maybe 15 meters long. Doesn't that imply their precision is, good enough for many demanding jobs? Does it make the fixed beam's absolute rigidity sometimes overkill?
That's a really important strategic point. Modern engineering has done wonders, no doubt. You have advanced damping systems, sophisticated thermal compensation, laser calibration on moving beams. They've narrowed that accuracy gap significantly.
So they can achieve high precision.
Yes. But fundamentally, you're often compensating for potential structural movement or vibration. You're using clever software and feedback loops to correct for a physical characteristic of the moving design.
Whereas the fixed beam is trying to prevent that physical issue from occurring in the first place through its sheer static mass and rigidity.
Precisely. So for the absolute most demanding applications, think ultra-high precision molds, optical components, situations where every fraction of a micron counts. That inherent structural integrity of the fixed beam still holds a real advantage. It's often the better choice there.
But for heavy roughing of large parts, or jobs where maybe 5 microns is perfectly fine tolerance versus 1 micron,
Then the moving beam is often excellent. It excels at high material removal rates on large components, or where the sheer size and weight capacity are the dominant factors rather than that ultimate last bit of absolute precision.
Okay, let's connect this back to the shop floor reality. Installing one of these giants, the machine itself is just part of the cost. The footprint it takes up and the foundation it needs, these are huge, hidden, or maybe not so hidden costs. And this seems to be where the fixed beam starts to look less appealing.
This is often the biggest practical trade-off. You're right. The moving beam gantry is actually remarkably space efficient for what it does.
Really? How so?
Because the machine's footprint is essentially just the bed area plus the gantry structure itself. All the x-axis movement happens within that defined envelope as the gantry travels over the bed. It's relatively compact.
Okay, I see. The machine contains its own motion.
Exactly. Now, the fixed beam gantry, that's a whole different story. It's often described as a real space hog.
Because the table has to move.
Because the table has to move its entire cutting length. So if you need to machine a part that's, say, 5 meters long, the table needs to travel that full 5 meters out from under the gantry.
Which means the total floor space required could be double the actual static length of the machine base.
Easily double, or even more, depending on the setup. You need clear space for that massive table to shuttle back and forth. In a facility where floor space is expensive or just limited, that's a massive disadvantage. You gain that nth degree of precision, perhaps, but you lose a huge amount of shop floor flexibility.
And that cost ties into the foundation too, right? What are the differences there? Because pouring concrete for these things isn't trivial.
Not at all. They're fundamentally different challenges. For the fixed beam, you've got that enormous heavy table and workpiece constantly accelerating and decelerating, sometimes at high speeds.
Right, that dynamic load we talked about.
Exactly. So the foundation has to be incredibly robust, deeply reinforced, specifically designed to absorb those constantly shifting dynamic forces without flexing or settling over time. It needs to be massive and stable, pouring, curing, ensuring that stability. It's a major civil engineering task that adds significant cost and time to the installation. Weeks, maybe months.
Okay, and for the moving beam, the part isn't moving, so.
So the foundation doesn't have to absorb those huge dynamic loads from a moving workpiece. Its main job shifts. The critical factor for the moving beam foundation is ensuring the absolute perfect, long-term geometric alignment and stability of the rails that the entire gantry travels on.
So it's less about brute force absorption and more about precision alignment over potentially very long distances.
Precisely. It's still a substantial foundation, don't get me wrong, but the engineering focus is different. Less about managing workpiece inertia, more about maintaining the positional accuracy of the moving gantry structure itself.
That's a really interesting distinction. What about maintenance? Does having that huge table moving versus the whole gantry moving change the long-term upkeep?
It does, generally. Maintaining something static is usually simpler. With the fixed beam, you've got that high-speed, heavy-moving table. That means constant attention to lubricating the guides, monitoring wear on those guides, checking the massive drive systems, the motors, the ball screws, or rack and pinions moving that mass. It's a lot of moving parts under high load.
And the moving beam.
Well, the workpiece area, the bed, is static, which simplifies things there. You still have the complexity of maintaining the gantry drive systems along the rails and the Y and Z axis, of course, but you don't have the wear and tear associated with constantly moving the workpiece itself. It's perhaps a bit of a trade-off, but eliminating the moving table simplifies one major maintenance area.
Okay, let's shift gears to something really big. Scalability. Imagine you need to machine something truly enormous, like a section of a ship's hull or a train car frame, maybe parts for a giant wind turbine. We're talking 10, 20, even 30 meters long.
Right, and this is where the fundamental design difference becomes incredibly stark. For parts like that, the fixed beam design essentially becomes, well, impossible, or at least economically and logistically completely impractical.
Why impractical? Just the table size.
It's the table size, the weight, the inertia, the foundation required. Imagine needing to machine a 20-meter long part. You'd need a moving table at least 20 meters long, probably more. Think about the sheer mass of that table.
Astronomical.
Astronomical. Then you need the drive systems powerful enough to accelerate and decelerate that mass accurately. And you need floor space, not just for the 20-meter machine, but another 20-plus meters for the table travel. So you're talking about a foundation supporting over 40 meters of length.
Yeah.
Capital costs, the energy consumption, it just spirals out of control.
It becomes completely prohibitive.
Utterly. Which gives the moving beam gantry an absolutely unbeatable exclusive advantage in this realm. It is realistically the only scalable option for extremely long or heavy parts.
Because the workpiece stays stationary.
Exactly. You mount the workpiece, the aircraft wing, the ship section, whatever it is, on a static floor plate or bed. There's virtually no practical limit imposed by the machine itself on the part's weight or its length.
So the x-axis travel, the length you can machine, is just determined by how long you make the rails for the gantry to run on.
Precisely. If you need to machine longer parts in the future, you can potentially extend the rails. You just add another section. That modularity, that inherent scalability, is the strategic genius of the moving beam design for large-scale work.
And that's why it dominates certain industries.
Absolutely. It's the go-to choice, really the only choice, for those massive components you find in aerospace, shipbuilding, energy generation, rail transport. For them, the ultimate capacity and flexibility far outweigh chasing that final micron of precision offered by the fixed beam.
Okay, so after this deep dive, it feels like the strategic choice really boils down to one fundamental question for you, the listener. What is your absolute priority? Is it that unwavering peak structural stability and precision, mainly for high-value but maybe medium-sized parts, that points towards the fixed beam?
Right. Or is your main driver ultimate size flexibility, the ability to handle potentially massive or very long parts, scalability for the future, and maximizing your shop floor efficiency? That points squarely towards the moving beam.
For those super high accuracy molds or dies, maybe the fixed beam's monolithic stability is still the gold standard.
It often is, yes. But for handling those huge, varied, and especially extremely long workpieces, the modular, space-efficient, and scalable moving beam design is really where things are heading for large format machining.
Which brings us to a final thought. Considering, as you said, the moving beam is clearly superior in space efficiency and scalability, and we know that modern engineering, the software, the compensation systems, are constantly narrowing that historical accuracy gap. It really poses a crucial strategic question for anyone investing long-term, doesn't it?
It does. The question becomes, how much longer will that absolute structural precision advantage of the fixed beam outweigh its significant limitations in footprint and its total lack of scalability for large parts, especially in such a competitive global manufacturing landscape where size and flexibility matter more and more?
That calculation, that trade-off analysis, that feels like what will separate the winners over the next decade of large-scale production.
Yeah.
Something to definitely think about.